So far we have discussed about groups and subgroups. Now we are trying to find devise some ways to determine whether a given set is a subgroup, and also we are trying to do some characterizations. Already we have seen one characterization earlier which said that a subset of a group is said to be a subgroup if it is closed under the operation of G, and also if it for every element there is an inverse. So we have done that already. So before we proceed to this theorem, let us briefly recall what's a group. So group is basically an algebraic structure. So it has a set and also a operation star which is defined on G, which has the following properties. That is, it will be closed. That is, for if you combine two elements in G, you will always get an element of G itself. A star will be always will be there in G, and also it will be associative. This means that if you take A star, B star, C, you can compute in any order. That is, it is equal to A star, B star, C, and also there will be an identity element E which has the property that A star E is equal to E star A is equal to A, and also if you take an A, you can always find an A inverse which has the property that A star A inverse is equal to E, which is equal to A inverse star A. So if this set G satisfies all these properties, so the set G together with the operation star will be called a group. Now what is a subgroup? A subgroup is nothing but a subset of a group G which has all the properties of a group. So a subset H of G which also has all the properties of a group. That is, it will be closed, it will be associative, it will have identity element, also it will have inverse of every element in H. So basically subset is actually a group in its own sense. So if you take the set of real numbers under addition, it's a group. If you can check all this thing. Similarly, if you take Z, the set Z, which is a subset of R, and if you take on the same operation, you can see that Z is also a group. So we call that Z is a subgroup of R. So this is the basics about subgroups. Now let us come back to this theorem. So this theorem is talking about a way to determine whether a given subset is a subgroup or not. Okay, so what is the way telling there? So it says that if the subset is finite, it is very easy to determine whether it is a subgroup. So how will it determine? It just says that if the operation is closed under this subset, definitely it will be a group. So let us just read the statement. It says that a non-empty finite subset of a group G will be a subgroup if and only if it is closed under the operation of G. So that is the characterization here. So please read this again. Just think about it for a second, and let us proceed to the proof. Okay, so since this is an if and only if condition, you have to prove it both ways. There are two ways to prove it. You will assume the first condition, you will prove the second condition. Similarly, you will assume the second condition, and then you will come to prove the first condition. So since this is an if and only if condition, you have to prove it both ways. It is very easy, but a slight amount of thought is required to do this proof. So let us just forward. Let's just go to it now. Okay, so what's the condition now? So let us define the setting now, basically. So okay, so suppose we have a group G together with an operation star. So we have to write A star B for every operation here. So instead of a star, I am just using the notation as AB. So I will use AB for writing A star B to make things simpler. So if I write A B, it means nothing but A star B. Okay, so let us take a group G comma star, and also let us take a subset H of G, okay, which is non-empty. Okay, so this is our setting. Okay, now what you have to prove? So first you will assume that H is a subgroup of G. So first you will assume that H is a subgroup of G. Now what you have to show? Just look at the statement. You have to show that H is closed in the operation. So H is closed under the operation in G. Okay, it's very simple because there is nothing to prove here as per se, because since H is a subgroup, it will obey all the conditions involved in a group. That is, it will be closed, it will have associative property, there will be identity element, there will be inverse element. So definitely closeness is one of the elements of being a subgroup. So definitely when H is a subgroup, it is always closed under the operation. So there is nothing to prove in the first stage. Now we are coming back to the second stage. What you have to prove? Coming back to the second stage, what you have to prove? You have to assume that H is closed. H is closed under the operation of G. Now you have to show that it is a subgroup. Okay, so this is the tricky part. It is a slight bit difficult portion also. Let us try to understand what you are going to hear. So here we are going to assume that H is closed under the operation of G, and we are going to prove that H is a subgroup. Okay, so what are the details we know about H? What are the details which we know about H? Yes, so basically H is non-empty and it is finite. So basically we know that H is non-empty and also it is finite. Okay, now we have to show that H is a subgroup. So what all conditions should we show? So what all conditions should we show? In order for H to be a subgroup, it should be closed. Again, it should have the associative property. Again, there should be the identity element. It should be there in H. And for every A in H, I have to find an A inverse in H. So these four conditions should be satisfied. Now, some of these conditions are very easy because already you have assumed that H is closed under the operation. So there is nothing to do there. First condition is already done. We have assumed the first condition. And again for associative property also it is very simple because after all H contains elements in G and in elements in G will have the associative property because AB into C will be equal to A into BC in G because G is a group. So since A, B, C are elements in H, they are ultimately elements in G. So this condition will be satisfied anyway. So this is also will be satisfied in the group in the subset of H also. So associativity property is also very trivial. Okay. Now the main step goes is we have to show that we have to show that identity element. We have to show that the identity E is there in H. Okay, so let us proceed to that. So before that, let us recap once again. H is non-empty and also H is finite. So these two assumptions are made here. You have to show that identity element is there in H. Okay, so very simple. Since H is non-empty, what can you say? Since H is non-empty, you can always find an element in H. Okay, I'll call this element as A. So there will be some there will be some element in H. I'm just calling it as AH. Okay, now what I'm going to do is that I am going to multiply each and every element in H with this A. So then just let me enumerate the elements in H. Suppose I can write the elements in H as like this H2 etc. Maybe Hn is there and also A is also somewhere lying somewhere there. So I am going to multiply each and every element of this H with A. So what will I get? I will get the set AH. Now what is the property of AH? AH is nothing but it will be AH1, AH2 etc. AA and also AHN. So I am multiplying each and every element of H with this A. So we are considering the set HAAH which is nothing but A into H where H element of H. So now you know that we have already assumed that H is closed under the operation of G. So basically that means that what can you say about that? So that means since H is closed, you can always see that A into H will always be there in H because H is closed. Also A is an element of H, H is an element of H. So when you multiply, you'll always get an element in H itself. So AH is always lying in H only. So that means every element of AH is lying in H. So you can definitely say that AH is a subset of H. Okay. So I don't know whether AH is equal to H or AH is less than or equal to H, but it is basically a subset of H because every element in AH is lying in H. So I hope this point is clear to you now. Now let us look at this closely. So when will AH will become strictly a proper subset? So I don't know whether AH is equal to H. Suppose we are assuming that AH is a proper subset of H. So when can this happen? This happens when we take these elements. So basically AH is formed by multiplying the elements of H by A. So AH1. So this set will be actually be strictly less than H when some AH1s or some AHIs will be equal to some AHJs. Because when some two elements are same, that means the original set, this set will be lesser than the original set. So when two or three elements are same, this means that this set will have lesser number of elements, lesser number of different elements than the original set. So let us assume that maybe AHI is equal to AHJ, I don't know, maybe for some I comma j. So let us suppose that this condition has happened. That is actually H has become a proper subset. So what will happen if you take this condition? So you know that basically H and G are all, H is a part of a group G. In a group G, cancellation laws will hold, which means that if AB is equal to, which means that if AB is equal to AC, B will be equal to C. So similarly, if I take AHI is equal to AHJ, I will get that HI is equal to HJ, which this is by means of the cancellation laws. So what does that mean? That means that each of the elements AH1, AH2, etc., AHN are entirely different. That means you have n different elements in AH. So what does that mean? Now you have a subset of H which has the same number of elements as H. So now we have a subset AH of H which has the same number of elements as H. And now we are considering only finite sets here. We are not considering the infinite scenario. So basically we have a finite subset of H as a finite set which has the same number of elements of the as the original set. So what does that mean? It just means that both of them are just the same. So that means here we have obtained that AH is equal to H. So I hope this is clear. It's very simple. What you are doing, since H is non-empty, you can get an element in H, A in H. You can multiply each and every element of H with this A. I am taking the set AH, and now you have demonstrated that AH is equal to H. So this much is there with us. Okay, now let us look at closely the set H and AH. So basically H is nothing but the set H. I am just enumerating the elements of H. So this is finite. This will be some elements will be like this. So H1, H2, etc. up to n are there. So how many elements are there? Okay. So how is this AH obtained? It is obtained by multiplying each of these H elements by A. So AH2, there will be A into A will be there. AHN will be there. Okay. So what is actually happening? What is happening is that this order of the elements are being changed. So when I multiply H1 with A, I may be getting some other elements, or maybe suppose AH1 will be equal to maybe some H3. So the order of elements which is written in AH has been disturbed because of multiplying with AH. So this actually AH1 will be equal to some H3, AH2 will be equal to some H2. So anyway, all the elements are there here, but they are written in some other order. Okay, I hope that point is clear. So AH is basically H written in a different order. Okay, so similarly, since A is an element of H, I can find some, maybe I can find an AHI for which this will become A. Is that clear? Because A is already an element of H. So when multiplication happens, so when I multiply some HI with A, I don't know what HI is, there will be some HI because you should get every element here. So when I multiply that HI with A, what I will be obtaining? A itself. So suppose I have taken that element as HI. So since this is reordering of the same set into different set, so that means when there will be some HI which when multiplied with A will give you the same element as A. So let us fix that element as HI. Now what is the specialty of this HI? It says that AHI is equal to A. But which other element has this property in this group? Already we know that identity element has the same property. So what can you conclude now? You can conclude that AHI is equal to A into E. Now what does this mean? This means that actually HI is equal to E, that is because of the cancellation property, A will get cancelled out. So I have got that the element HI was actually the identity element. So this establishes that the identity element is also there in H. Okay, so how is this established? Think again once more. How we have enumerated H. H is the basically H written in a different order. This is obtained by multiplying each and every element of H by A. So we have multiplied it. So it has been rewritten. So when the process of rewriting this, we can always find an AHI. We can find an HI which has the property that A into HI is equal to A. This should happen because AH is equal to H. So I should obtain every element of H from AH itself. So there will be some HI which has the property that AHI is equal to A. But also we know that identity element will also has the same property, that is A is equal to A. So when you compare these two elements, we can always conclude that AHI is equal to AE, or in other words HI is equal to E, which means that identity element was in fact in part of H itself. Okay, so we have gone halfway through. Then one more step remains, that is inverse. Okay, so let us look at the discussion now. Already we have H here. Okay, so here we have enumerated elements H1, H2, etc. We have seen that AE is also there in H. Already A is there in H also up till Hn. So there are many elements in between also. So we are taking this AH. When I take AH, I will get this as AH1, AH2, AE will be there, which will be our A itself. Similarly, A into A, AHN. Okay, so when you take this using the same idea as before, you can see that. So here somewhere E should also be present. Okay, because in H E is there. So for some element, for maybe some, for example, maybe since I called it AHI before, I'll call this as AHJ. So for some H, I should obtain AH as E, because E is also part of H. So in somewhere there should be an element hj for which ahj will give you the value e. Okay, so now we are going to establish that this hj is actually the inverse. What is the property of inverse? The property of inverse is a inverse is equal to e, which is equal to a inverse a. So we are going to establish that this hj is in fact the inverse element. Now we have got the first part of this, that is ahj is equal to e. Now we will establish that hj into a is also e. So before that, what I am going to do is that, so we will just consider this hja into hja. We are just going to evaluate what this is. So this is by associative property hj into, you can compute in any order, you can change the order of computation. So hj into ahj into a. Okay, now what is ahj? Ahj is, by definition, it is e, so it is nothing but hjea, which is actually equal to hja. Okay, so we have obtained that. What have you obtained? We have now obtained this as hj into a into hj into a is nothing but again hja. Okay, so this, what does this signify? This is signifies actually this hj into a is an idempotent element, and you know that in a group only one idempotent element is possible, that is the identity. So this means that hja is equal to e, or in other words, you can also do it like this. You can write hja, which is equal to nothing but hja into e, and now you can use the cancellation laws to cancel out these two elements. So then also you will obtain that hja is equal to e. So now we have got that ahj is equal to e and also hja is equal to e. So when you chose a, you have obtained an element hj which has this property. That means hj is the inverse of a. So for every a, you have an inverse. So this was a particular a. If you take some other b, again the same argument will follow. Before that, you will be getting some other element. So similarly, for every element also you can find inverse like this. So what have we got till now? We have got that this has inverse also. So this set H has identity element is present, and if you take an A, you can also find its inverse, which was Hj, or actually A inverse. So H has all the properties of a subgroup. Closeness is there, associative property is there, identity is there, inverse is there. Therefore H is a subgroup. So what is the condition here? Let us look at the condition once again. A finite subset of a group is a subgroup if, what's the condition? It is just closed under the operation in G. So this is an important proof. I hope it is clear. Okay, thank you.